So last lesson, we met the idea that we could draw a graph of velocity, and we had a little play with what we could do with it, but we're really going to develop the velocity time graph today in quite a mathematical way. So clear your head, make sure that you're okay with it. But we're just going to make sure that you're okay with last lesson first, which is why Spiral is with us today. We are going to just do a couple of questions from last lesson just to make sure that you're okay with it. So here's the first one. A car is traveling at 21 meters per second, and 16 seconds later, it's traveling at 33 meters per second. Could you please tell me what its acceleration is? And pop it onto Spiral when you are ready to do so. I'm going to give you what you want, 60 seconds. So let's have a little look at how to do it. We've got a change of speed is 12 meters per second because it went from 21 to 33. The time that took is 16 seconds. So on your calculator, you need to do 12 divided by 16, which gives you a numerical answer of 0.75. But then you need to remember to put the correct units on it. So the ones that have given me the correct numerical answer have generally given me the correct unit as well. People who are getting the wrong number answer are also getting the wrong units. So I guess there is an element of practice that we need to do there, but that's okay. I knew that, and we will be doing that next lesson anyway. Okay, let's do another question. This time a graph. So this one doesn't need to go on Spiral. Just think about it in your head. Here is a velocity time graph. Could you just, in your mind, describe each segment of that graph? There are 1, 2, 3, 4, 5 different parts to this journey. Just settle on how you would describe those 5 parts in your head. You have 1 minute now. Okay, let's go through it. So the first section of the graph here is an acceleration because the velocity is getting bigger and bigger and bigger. And we can also say that it's a constant acceleration because it's a straight line, which means that it's increasing by the same amount every second. And also, because the velocity is positive, we can say that the object is moving away from us. The horizontal part of the line means that the velocity is neither increasing nor decreasing, so that's a constant speed. And it's a positive value of the velocity, meaning that it's a constant speed in a direction that's away from us. Here, the velocity is reducing back down to 0, so that's a deceleration. But the velocity is still positive, so it's still traveling away from us. And it's still a straight line, meaning that it's changing by the same amount each second, and therefore it's a constant deceleration. Although it's the same line that carries through the axis, something different happens because the object actually stops moving altogether at this point here when the velocity hits 0. But then it starts traveling in the opposite direction. The values of velocity are now negative, which means it's traveling back towards us. Again, it's increasing in numerical value. So it was 0 where the laser pointer is, but as you go along the line, it's getting further and further and further up the velocity axis, just in a negative number rather than a positive number. So this again is an acceleration. And again, it's a straight line, meaning that it's changing by the same amount each second. So it's a constant acceleration. And then for the final segment of the graph, we again have the velocity reducing back down to 0. So it's a deceleration. Again, it's a straight line, so it's a constant deceleration. And the values of the velocity are still negative, and therefore it's still traveling towards us. Interpreting velocity time graphs is generally more complicated than interpreting distance time graphs because the aspect above the time axis is kind of almost a mirror image of what's happening below the time axis, and you just need to be careful about that. Okay, let's move on to today's lesson. So last lesson, we noted that the acceleration had a formula, but we ran out of time before I could share that the formula corresponded to the gradient of the graph. So just like the gradient on a distance time graph refers to the velocity, the gradient on a velocity time graph gives us the acceleration. And therefore, steep lines mean a very high rate of acceleration, and shallow lines a really small rate of acceleration. Now, the angle, whether it's sloping upwards or downwards, also tells us whether it's an acceleration or a deceleration, but you just have to be very, very careful about how you interpret that. So here on the graph in front of us, we have got positive velocities getting more positive, and therefore that's an acceleration. Oops. And here are positive velocities getting a smaller positive number, so this is a deceleration. However, if we go below the time axis so that the motion is towards us, here are negative velocities getting more negative, and here are negative velocities getting less negative. So the accelerating and the decelerating are still apparent, but you can't just go with a simple sloping downwards, because here we've got sloping upwards is accelerating, but here sloping upwards is decelerating. Sloping downwards is decelerating here, but sloping downwards is accelerating here. You just have to be really careful about interpreting the sign of the gradient, depending on whether it's above the time axis for positive velocities or below the time axis for negative velocities. So that was just a little bit that I didn't have time to slot in at the end of the last lesson. We are going to spend more time next lesson practicing all of these things. So if you're feeling a little bit uncertain about that and you feel like you need some practice, it's fine. I've built some practice in and we will get that in the near future. Okay, let's move on to the new content for today's lesson. We've so far said that you can get the velocity from a distance time graph by using the gradient. Actually, now what I'd like to show you is that you can get the distance from a velocity time graph, but not via the gradient, because we used the gradient, as we've just seen, for the acceleration. But there is an aspect of the velocity time graph that does reveal to us the distance traveled. So what is that? Well, here it is. So let's start with a simple example. Here is an object that is traveling at a constant velocity, not accelerating, not decelerating, just the same number of meters traveled every single second. Let's pretend that it's traveling at 5 meters per second, and it does it for 10 seconds. So the question is, how far did it travel in that time? So we know full well that the distance traveled is speed times time. It's 5 meters per second for 10 seconds, which means we know that the distance traveled is 50 meters. The question is, which aspect of the graph shows us that the distance traveled is 50 meters? And what the aspect is not the gradient of the line, it's the area trapped beneath the line. So if you just shade that rectangle in, you can see that that rectangle has a height of 5 and a width of 10. And you know from maths that the area of a rectangle are the two sides multiplied together, and 5 times 10 is 50. And so the area of the rectangle corresponds to the distance traveled. Now you might just think, oh, well, that's a fluke. It's just a coincidence that the area is the distance traveled, that 5 times 10 is 50 and 5 times 10 is 50. That's just the way it works. Surely it doesn't work for random areas. Well, no, it does. So let's have a little look at an accelerating object. Again, let's say that it gets to a distance of 5 meters, a speed of 5 meters per second after it's been traveling for 10 seconds. And what I am wanting you to believe is that the area of this rectangle is the distance traveled. It's obviously not traveled as much as it did before because it was traveling at 5 meters per second every second in the first example. This one started off much more slowly. It doesn't cover as much distance at the beginning. It's only traveling at 1 meter per second, 2 meters per second, 3 meters per second. So it's much slower at the beginning. So it can't possibly travel the same distance as a car that was traveling fast all the time. So we know it's going to be less. And the area of this triangle is less than the area of the rectangle. But does it have to be the area of the triangle? Well, it does, because if you think about it, in order to travel for 10 seconds, I have to travel for 0.1 of a second and 0.2 of a second and 0.3 of a second and 0.4 of a second and 0.5 of a second, all the way up to 10 seconds. And in actual fact, really all that is a whole load of individual little rectangles. Now, for the sharp-eyed amongst you, if you haven't got a very tiny screen, you will notice that there is a tiny discrepancy in areas between all of those rectangles and the triangle. There are some tiny little white bits beneath the blue line above the grey bars that have been missed out. But the only reason that they've been missed out is because I have only split this up into about 20 rectangles. The narrower I make the rectangles, the smaller those little white missed out bits become. And in fact, if this becomes a continuous journey where I look at it in like billionths of a billionth of a billionth of a second at a time, all of those little white bits become insignificantly small. And we really do have the area of the triangle. So now we can use this information that the area trapped underneath the line of a velocity time graph is the distance traveled. So in this particular case, we've got the area is a half base times height. A half times by 10 times by 5 gives us 25. So this object actually travels 25 meters in the time of 10 seconds. So the bit that I need you to write in your book, possibly sketching the graph that's on the screen in front of you by way of illustration, I need you to copy down the bold writing, please. In general, the area under a velocity time graph is the distance traveled. And then if you want to, do a little sketch by way of an example. I am going to give you 1 minute to write that down. So we've already noted that we have to be careful with an interpretation of the gradient for the acceleration, because what happens above the time axis for positive velocities is a little bit different to what happens below the time axis for negative velocities. And that is true of this as well. We need to remember that any areas that are above the line are in a forwards direction, and any areas that are below the line are in a backwards direction. So we need to treat the two areas separately. We can't just do them at the same time. So here we've got a 5 times a 6 above the line. And we've got a 2 times a 9, the 9 from the difference between 6 and 15, below the line. So what does this graph show us? This graph shows us that the object traveled at a constant velocity in a forwards direction for 30 meters, and then did the world's most insane deceleration and then acceleration again. You can't really have a vertical line on the velocity time graph, but it makes working out the areas a little bit easier. You can't really go from 5 meters per second to 0 meters per second to minus 2 meters per second in 0 seconds. That's not physical. That would involve an infinite acceleration. But for the sake of working out areas easily, what this shows us is that the object travels 30 meters in a forwards direction, and then after its insane deceleration acceleration, it then travels 18 meters in a backwards direction. So if the question is, how far did the object travel? Well, you need to be really crystal clear on exactly what the question is asking you, because the actual distance that has been traveled is 48 meters. The object traveled 30 meters forwards and then another 18 meters coming back again. So if you were walking that would be you walking 48 meters. You walked 30 meters there and then 18 meters back again. So the actual distance that has been traveled is 48 meters. You add the two areas together. However, if the question is more, how far from home are you when the journey finishes? Well, you went 30 meters there and then you came 18 meters back again. So actually you have ended up 12 meters from where you started. Now, we have a special word in physics for the difference between the beginning of a journey and the end of a journey. And that word is displacement. So in this particular case, we can say the distance traveled are the two areas added together, 48 meters, but the displacement is the forwards take away the backwards, so that we can see that we only ended up 12 meters from where we began. So again, I would copy down that diagram if I were you, and I would copy down the latter two paragraphs, the one that says total distance equals and displacement is 12 meters. So copy down the picture, copy down the last two sentences. You don't need the first paragraph. Okay, that is your time up. Let's move on to the next thing. Okay, could you please take a really good look at this graph? So constant acceleration away, constant speed away, constant deceleration away, stationary, constant acceleration towards us, constant deceleration towards us, stationary. Get used to interpreting the motion at a glance. But I want you to do some calculations. So here we go. Here are the numbers that you're going to need. The acceleration lasts for 2 seconds and gets up to 10 meters per second. The constant speed lasts for another 3 seconds. And then the constant deceleration lasts another 4 seconds. The acceleration in the backwards direction lasts for 3 seconds and gets up to a speed of minus 7.5 meters per second, or velocity. And then after another second, the journey comes to an end. So there are your numbers. I'm going to need you to do some quick calculating on your calculator, and then I need you to post the numbers to Spiral, please. So here we go, just to check. First of all, can you calculate accelerations? So could you please, on Spiral, 30 seconds, what is the acceleration for the first part of the graph? Again, the acceleration is the change in the velocity. In this case, it was from 0 to 10. So the acceleration is 10. Sorry, the change in velocity is 10 divided by the time taken, which is 2. 10 divided by 2 is 5. And then we've divided meters per second by seconds. So your unit is meters per second, which you can write as m/s2 if you want to. It's also, you can think of it as the gradient of the graph. So if you're more mathematically inclined, the gradient of the graph is the change in y divided by the change in x. So 10 divided by 2. Okay, let's do another one. 30 seconds. You shouldn't need 30 seconds for this one. What's the acceleration for this part of the graph? Okay, so this object isn't accelerating. The velocity is 10 meters per second at 2 seconds, and then it's 10 meters per second at 3 seconds, and then 10 meters per second, 4 seconds, and still 10 meters per second at 5 seconds. It's neither getting faster nor slower. It's not accelerating, it's not decelerating, it's just traveling at a constant velocity. The acceleration is 0. Okay, let's try the next one. Could you please tell me what the acceleration is for this portion of the line? Remember, it's change in velocity divided by the time taken. Okay, so I had lots of 2.5s come at me, but remember, it's lost velocity. It was 10 and now it's 0. So the change in velocity is not 10, it's minus 10. It was traveling at a positive speed, now it's traveling at 0. Its change in velocity is a reduction of 10. So when you do the change in velocity divided by time, the change in velocity is minus 10. The time is 4, so minus 10 divided by 4 is 2.5, but it's minus 2.5. Okay, next one. Have a go at this section of line. It's an acceleration below the line. We've got that it begins at 0, and then it gets faster and faster and faster and faster. The change in velocity here is 7.5 because it's getting faster and faster and faster, but in the backwards direction. Okay, last one. In this particular case, it was traveling at minus 7.5 and then it was traveling at 0. So in this particular case, it is decelerating. Okay. That's some acceleration practice. Let's have a go at some distance practice. Could you please tell me how far the object traveled during the first 9 seconds? And I guess this will be easier if you remember from maths what the area of a trapezium is as a formula. Otherwise, you're going to have to split it into 2 triangles and a rectangle. So to work out the area of a trapezium, you average the parallel sides. So this one is 9. The one at the top is the difference between 5 and 2, which is 3. So the average of 9 and 3 is 6. And then you multiply by the height, which gives you 60. Alternatively, you could have done the area of the triangle. This is a half base times height, so that's a half times 2 times 10, which is 10. This one's a half times 4 times 10, which is 20, so that's 30 altogether. And then we've got 3 times 10 in the middle, which is another 30, which gives us 60. Okay, try the triangle at the bottom instead. So the height of this triangle is 7.5. And half of the base is half of 4, which is 2. So 2 lots of 7.5 is 15. Okay, so the top bit was 60 and the bottom bit was 15. What I would like you to tap into Spiral now, please. The top bit was 60, the bottom bit was 15. What is the total distance traveled, please? And it's just 75 meters. We traveled 60 meters in a forwards direction, and then we traveled 15 meters in a backwards direction. The total direction traveled was 70. The total distance traveled was 75 meters. What about the displacement? Could you tell me what the displacement is, please? This is how far from the beginning you ended up at the end. You traveled 60 meters in a forwards direction and 15 meters in a backwards direction, which means you finished up just 45 meters from where you began. We've got one last little thing that we're going to finish off in the last 10 minutes today. And really all I'm going to do is introduce it to you, and we're going to have to practice it as part of our wider practice that I've already told you we're going to be doing over the next couple of lessons. So if you choose to do an A-level in physics, we take the concept of everything we've just done with graphs and we turn it into algebra. Because by the time you get to A-level, we expect that you're, very, very comfortable with algebra in a way that you're just learning to be, some of you now. And so we don't want to bamboozle you with a whole load of algebra at GCSE. But just to give you a glimpse of where this is going, there is one tiny little thing that we are going to just give you a hint at about what's coming up if you chose to do your physics at A-level. So what we can do is we can take the quantities that are on the velocity time graph and we can award some algebraic variable names to them. So for instance, the area under the graph is the distance traveled. It's traditional to give that an S rather than a D. I don't know why. We'll just go with the flow. We use an S instead of a D. The beginning velocity and the final velocity are usually referred to as U and V. So V for velocity, obviously, and U because it's the letter before V in the alphabet. The gradient of the graph gives us the acceleration, which we use an A for, and the time that the journey takes is T for time. So once we have got these variable names, we can then use the information that the gradient is the acceleration to create an equation that links the change in velocity, which is V minus U, and we can divide that by the time, T, and that's equal to A, the acceleration. And we can also write an equation for the area under the graph. So S is equal to, and we could write down some rules involving U and V and T to get the area under the graph. And we do that at A-level. It's an activity we do early on in the course. And when we do that, we arrive at a set, when we finish, the set of algebraic equations that when you have them all in front of you, there are 4 of them. When you've got this set of equations, you don't actually need the velocity time graph anymore. You can just use this set of algebraic equations. They're called the equations of motion. Now, we're not going to go there at GCSE. We're not going to algebraify all of this. We want you to learn about velocity time graphs at GCSE so that you can then use them to do the algebra application at A-level. So this is your stepping stone year where you learn about velocity time graphs. So I don't really want to go into the equations of motion now. However, in the AQA course, your AQA examiner has decided that they would like you to at least meet one of the equations of motion. So if you are mathematically minded, you could try your luck at writing some equations for the gradient and the area and see if you can put them together to work out this equation here. The rest of us, we're just going to memorize it. Or not even that. This one's given to you on the formula sheet. You get a formula sheet with 7 equations on it that are deemed to be the ones most difficult to remember, and this is one of them, probably rightly so. So this equation allows us to work out the missing one when we've got the other 3. So for instance, if you didn't know what the final speed was, but you did know what the beginning speed was, the acceleration and the distance traveled, you could put all the numbers into this equation and get out the final velocity. So I'm just going to finish today's lesson with a single practice question on this. So I just need you to quickly write down in your book, underneath what we've just done, write v squared equals u squared plus 2as and put it in a box. And if you're going to forget that u is the starting velocity, maybe label it. And if you're going to forget that s is the distance traveled, maybe label that. And then we're just going to finish off with one last question. So a car is traveling at 21 meters per second, and then it accelerates to 33 meters per second. This is our car from the first example at the start of the lesson. How far does it travel? So there's your equation again, v squared equals u squared plus 2as. Take the numbers, compare them to the variables in the equation, and try and dig out the distance traveled, which is s. So 1 minute left. Here's a hint in case you are struggling to do the rearrangement. Here's the next stage in case you're struggling to assign which variable's which. Last little bit is just to tap the numbers into the calculator and you should get an answer of 432 meters. Okay. The lesson on acceleration and then this lesson about the gradients on velocity time graphs and the areas under the lines and this equation at the end. I actually don't think there's anything any harder than that. And although the rest of the topic is, again, fairly mathematical and will tax you a little bit in places, I don't think any of the rest of the topic will tax you as much as the last couple of lessons. So we are going to have to factor in a couple of lessons now to just doing lots and lots of questions to make sure that we're comfortable with this. And we'll begin that next lesson.